right, and come back to me halfway. Shut your computer, please, now. And I would write some of this information either in the back of your lab sheet that you've been working with, just so you have it in front of you or someplace else. So I don't want to confuse the computer, so hold off on your Google Docs now. All right, so chromatography, I only need about maybe 10 minutes up here before your lab, okay? Chromatography is a physical method of separation, right? So are we making any chemical synthesis? No, there's no chemical reactions here, period. It's a physical means of separating. And there's like gas chromatography, paper chromatography, liquid chromatography, everything chromatography. There's so many different types. So what we are doing today is what? Paper chromatography. And what do we call the paper? Well, no, it's not good to put, like, what phase do we call the paper? The stationary phase, because it's not moving. What do we call the solvent that we're utilizing? The mobile phase, because it's moving, right? So it's very logical in how we name our phases. A couple of other separation techniques that are useful, and there's like a pre-lab question regarding baking soda or baking powder. We know a couple that we use like really almost every lab. Filtering. Filtering is going to separate what kind of mixture? Solid and liquid. Distillation, which we won't do here, but you would do in organic in college. You deal with differences in vapor pressures or boiling points. And so if you have a liquid combo, this was, I'm not sure what that was, supposed to be a round bottom flask. Round bottom flask. I wrote one of these the first day in organic. It was good stuff. Liquid 1, liquid 2, and liquid 3. If they all have different boiling points, and I start to heat this with a Bunsen burner, which one's going to boil off first? The one with the lowest boiling point. It comes up through, it's liquid in this phase, it evaporates, it goes through a condensation tube. So what is it doing in the condensation tube? Condensating or condensing. And so it's going from its gas phase down to its liquid phase, and then it drips into another flask that you capture distillates off of. This is also how any distillation is done. And then can you guys name any other physical means of separation? This is gravity filtration right here. Can I get one? Decanting is one. Decanting is where you take the liquid-solid combo, but instead of filtering through a filter, you use like a glass stirring rod and you tilt it, and so the liquid runs off, the solid stays behind. What's another property? So like basically these are just utilizing different properties and isolated substances based on their differences in properties. This one's basing off of like literally state of matter. This one's basing this separation based off what? IMFs or solubility. Distillation's basing off of boiling point. Decanting against basing off of states of matter differences. Any more? Magnetic separation. That's a neat one. Yeah, okay, we'll do some more of those later. But really, I just wanted you to know chromatography, the big difference was. And then you guys know what your purpose is. Okay, this is the piece that we did not get to do yesterday. It's the first question. If you open up your packet, pre-lab guiding question simulation part 1. Open up your packet, first page. So what I want you to know, so that you can understand the particulate nature of this, is why are we using paper, and what's happening on a particular level with the paper and all the stuff we're adding together. So here's our chromatography paper, and we're starting the solvent low. What's very important for the I didn't add this in your procedural stuff, I was going to tell you today. What's very important is that the ink spot, or whatever the spot, the food coloring mixtures that you guys add, you're not going to do 2 next to the, you'll just put 1, but you want to make sure your solvent line is below the dot, because if it's above the dot, what happens to the dot? It just goes in the solvent and hangs out. It doesn't actually run with the mobile phase. So you definitely want to make sure your solvent's below. But then, just in general, I want to know why this happens. So why does water creep up the paper, assuming water is the solvent that you've selected? Explain this, draw this as a molecular attractions. How about talk about that first, okay? Go. I want to hear some keywords. Marcus, where's your group?
Paper, I don't have that high solid.
You should have it from a couple of days ago. This is not one left. This is Emily's. All right, give me some keywords and back to me. 3, 2, 1. Now's group. Capillary reaction. Okay, so that's a big word, but let's narrow that down to what that actually means. Maybe somebody else can pick up from here. For team this area, give me something.
Like rises up to 2 because of attractions.
Attractions. Okay, so capillary reaction and attractions. What kind of attractions would help it stick to the paper? So I want you to be cohesive with your neighbor. Okay, so that means that you're going to be like sticking together, like and like and like and like is all going to stick together. Like water is cohesive with itself when it forms a droplet. When is water adhesive? Sticks to other things, right? Non-self molecules. So which level of attraction is happening with the paper? Adhesive properties or adhesion. And then with water to water, because obviously water's following water up the paper. So what property or what characteristic is that? Cohesion, right? Okay, so I'm going to show you in diagram, because I think this makes a lot more sense diagram-wise. This is just cellulose. It's just like a big carbohydrate. What is one of the functional groups you're noticing? Say again? Alcohols. Okay, sorry, I heard a couple of things. So here's an alcohol group here, here, and here. All right. Water being the solvent is going to do what with those? No. Attract. Do not call a hydrogen bond a bond. We know it's not a bond, right? So what's happening here? Attracting via hydrogen bonding. We literally don't call it a bond though, it's just hydrogen bond attractions. So we've got a lot of water attracting, and as it goes and it travels on the paper, of course, as we up, it's because of the capillary action of cohesion and adhesion. So you have, I thought this image was better. You have, I'll let you read this first so you can see the legend. The little dark, or the black squares are more polar molecules that are like, of course, within the dye or the mixture. And then the yellows are the more non-polar molecules inside of the mixture. So take a second and observe, see what's happening. All right, and our solvent is what here? So, okay, so this is cellulose, right? You can see this little OH is hanging off. What is staying attracted to the cellulose up here? The black, right, the polar molecules. So that's inside of the solvent. Let's say it could be water, it could be a non-polar solvent. This is the pink line here is representing the polar solvent carrying those polar molecules. So that's going to kind of hang really close to the cellulose very early, so it does not travel very far because it's very attracted to the stationary phase. And then the non-polar solvent, and this is just laid on top of each other, they're not together in the same container, this is just two images on top. Your non-polar particles inside of that solvent are going higher and higher and higher. Why? So why are they able to travel farther? Okay, so because they're not attracted to the stationary phase. So if they were attracted to the stationary phase, they stick. But because they're not, they're traveling along with the capillary reaction that's naturally happening anyway. And so they travel higher. So then as you note that, you would then need to indicate the RF values. What's the RF value indicate? The distance the solute, right, the particle of interest, travels compared to the solvent. And that solvent front, you have to look for very closely because obviously these things are clear. So on when you're observing this in the lab, like make a pencil mark where your solvent front ends upon you getting your results so you can actually do that measurement. So that would be here and here for these two separate experiments. We okay? Yeah? Okay. One more thing. Oh, this is the pre-lab we're not doing. These questions are the ones that we did not do yesterday because you guys were working on the simulation, but you're totally fine to do these today. There are 5 of them, but I would wait till you set up your lab experiment because this will take a moment to sit, and we're not going to sit here and look pretty. We're going to do these questions, okay? And these can be found in the first page. I'm getting a lot of text messages right now. I think these are all updates from the app from you guys. And okay, good, thank you. So these are going to be completed shortly. And then before we move on, let's identify these because you were supposed to do that just a minute ago. What are the functional groups on the blue? Shout them out, come on. Anything you recognize? Okay, well the nitrogen itself isn't a functional group. You might want to look up some of those if you're unaware, but I think you could definitely tell me the IMFs that each of these color-coded areas could interact with. What can this interact with? Via. So there's probably so there's a double bond, single bond. There's probably a lone pair here. So there's no N to H. So is this a polar region or a non-polar region? Polar. So what's the interaction going to be? Dipole-dipole. Unless there was an NH, then we could say hydrogen bonding. And what about all these groups here? How can they interact? What kind of area is this representing? Again, polar. Like it's definitely got a kind of a trigonal appearance to it, and you're gonna have some electronegative groups out here, partial negative. So this is polar as well, all the way across. What IMF would be at play? Dipole, good. And then like a lot of these areas here would be what? One dispersion all the way, because those are all nonpolar, right? So what you need to indicate or think about is in your solvent and solute interactions, which ones are the strongest, which ones are the weakest, and it's very cumulative, so you can't just look at one half of the molecule, you've got to look at the whole shebang. But a lot of this evidence would be hypothetical until you get the data, and that data will prove to you which ones had the better attractions and which ones had the least attractions. That's what we have to collect the data today. Okay? And then hexanes are off, I think, out of the picture. I don't think anybody selected that. They're not so friendly. And then lastly, these are our options for solvents. What are the functional groups we're noting? Alcohols, so it'll interact how? You guys know this. You gotta talk to me. So there's an alcohol group, and how will an alcohol group interact with other polar things? Hydrogen bonding, right? Same thing here. Water, hydrogen bonding, and then acetone, dipole. There's also one more. These are the most predominant forces, like the strongest forces. What can this side of the ethanol do? LDF. This side of the propanol do? LDF and acetone. LDF. So we have some interactions that we need to consider. This is kind of similar to the IMF lab, the boiling or the evaporation lab. The big point, and this was I need to review this with you guys again, is that we have data that supports that sometimes hydrogen bonding attractions are not as strong as a really long non-polar chain interacting via London dispersion. Sometimes London dispersion is the strongest force if there's a lot that's happening compared to one hydrogen bond. So we always rank hydrogen as the strongest attraction. Independently, yeah, but when you have a cumulative molecule interacting with 15 IMFs, you've got to consider the whole picture, okay? So that might be something you speak of in your conclusion here. And I think we've discussed what we needed to here, okay? So let me show you what we're doing in the back. Come on, get your groups together and clean the space. We will have to share lab stations because I'm just going to be part of this. Leave your stuff on the desk for me. There's the reading practical day one demonstration and reading practical. You guys come out of place, share the lab station. There's a space, there's a camera on that side and something on this side. All right. So Gabby and Christian have the lab station because they have people. That is big. How about never mind, they didn't hear say you guys hear Okay, so basically I told you a quick orientation on what I think is the best way to set. The beakers are great because you can set these like big test tubes in your beakers at an angle, and it'll keep your paper still upright. Obviously, these are not going to fit in the test tube rack, so don't try. Don't put it in the beaker because you'll use a lot more salt than you need to, and then your paper starts to kind of droop down, and then you have to start over because the ink got into the water and solvent. So this would be beneficial to use, but you can make sure everything is at constant, so you use the same size. I'm calling these chromatography tubes. Use the same size chromatography tubes so that you're not having any differences in surface area contact. I have isopropyl alcohol, 91%, so it's got a little bit of water in it. 95% ethanol, chromatographic solvent methanol, and then 100% pure acetone. All you're getting is the tiniest size you can get. Like, don't you get a whole drop from a pipette. So just you can take the pipette and you can just touch this and touch your paper. Okay? So you need to know where you're starting with, so you need to make a start line and finish, make a finish line so you have the distances pre-described. And then you have chromatography paper. It's a little curly, but what you want to do is you don't want to touch it with your hands on the surface. You can touch the edges and kind of straighten it out a little bit, and then that's how you're going to manipulate the paper so you don't get your oils on it, because your oils are obviously not polar, create some differences in data. Make sure these are all the same size. Okay? The other solvent is water. I think you can figure that one out. Any questions? Let's get set up. You have 10 minutes to set up, okay? You guys can use your own beakers. I got 8 out. You guys can use your own beakers. Also, you can put your own parafilm upon setting your paper into solvent. Parafilm will go on top to keep the operation rate low. Remember, you are only allowed how much of each solvent? 20 mils. So if you get a graduated cylinder, right with you, you can go ahead and get your 20 mils. In case you don't need all 20 mils, because I highly doubt you do. I mean, you guys see how small those are. You can use less than 20 mils, and we can run 2 trials of each, because some of your data may be not so good the first time. Okay? Please don't take more than you need, so you don't need much.
Is it 20? It's fine. This one is really
You can cut the chromatography paper down to size if you think it's too long. That's not a worry at all. I need all hands on deck, so if someone can go ahead and get a pipette to go ahead and dip into the dye, someone can do that. My only word of caution is do not use any pen No pen on chromatography strips. Pen is a mixture. Graphite is not. Pen will affect your results. Only graphite. Why do you think is that true?
The longer there is, the better it
You don't have to put it on.
Alright, you have about 5 more minutes to get set up. You should be very close to set. So I'm just going to borrow Christian's as an example. He touched the whole entire end of the pipette there. I think this also worked fine. A little smaller would be fine. But like a teeny tiny drop may not give you very clear results. So you can always err on the side a little bit more. I'll stand here with my pipette. Go. Dip and go. Regular action. Oh my God. I think that one. I think if you
Pretty sure that this cannot start. Oh no.
Last one to die. Last one to die. You need to parallel your top, so your top to be solving is going to be on. Parallel film. Parallel film. Do not jostle your solvents, or you will accidentally get your dyes, and they'll be gone, coming out. I mean,
Take this.
You got 5 people in your group. Let's go.
I went all the way over there.
I need to like hold these up.
All right, while you're waiting and watching, you are answering these questions in your Google report. You're answering these questions in your Google report.
Water.
Yes.
What?
Send somebody to come write the color that travels the farthest on the board. Send someone to write the color that travels the farthest on the board.
I'm putting pink for this one too.
Alright, I need you back in the front in 1 minute. 1 minute.
So this is the farthest traveled, right?
What?
This one's the farthest traveled.
Yeah, it's basically your last color.
Oh my god, it went the farthest.
Your highest.
Yes, please.
Hey, did you look at water? Or acid?
They're both blue.
Well, Gigi said it was
No, blue went the farthest. Did not. We can acetone.
Alright, 10, 9, let's go, folks, if you're chilling.
we just writing randomly, like random spots on the board?
Acetone is isopropyl. No, I Googled
Where
it.
did you get them from?
I'm not that smart. I gotta adjust mine.
Well, okay.
That's fine. Hope my fit's in the way. See if I can. It's doing good. Work it up.
All glass raised up. Pretty acetone. You want us to make like a new line?
Just take right here.
My bad. I was listening to what I was using yesterday and I saw one.
Or she distracted myself faster.
4, 3, let's go. You should have all your glass put up at this point. Don't leave anything on the desk because I have the last thing to mess with stuff.
Acetone is isopropyl. Somebody said acetone is isopropyl. Someone just
Two, bring me your yellow sheets here. Bring me your yellow sheets here. Here you go. I need data on the board. 3, bring me your yellow sheets here, please. Christian, can you write this for me? Oh, and Gabby. That's your registration stuff. Gabby, registration stuff.
Oh, do I need to bring you that
It
sheet?
said suggested to be due today. If you, for some reason, don't have it today, that's fine. Bring it tomorrow. 2, again. Please stop forging your parent signatures. Just bring it tomorrow.
I'll take that.
2, find a seat, find a seat. 1, did nobody do isopropyl alcohol? I was just wondering. It wasn't like a mad at you. Just making sure. All right, Ian, come back to me. Look up here. 3, 2, 1. Ready? So, according to acetone's group, it looks like everybody agrees that blue had the highest RF value, meaning what? So if blue's traveling with acetone, it's like pulling it along with it. So acetone's going, blue's coming with it. Why? It has the highest attraction to acetone. Why? Acetone has a what on it? What's the C double bond O? A ketone, which has the ability to have what kind of attractions? No, there's no hydrogens on carbon and oxygen, guys. Dipole, right? And then it's got 2 CH3 groups, 2 methyl groups on it, so it's got some London dispersion. You would need to explain that thoroughly. Okay, compare that to the blue structure, of course. Nobody liked ISO, okay. Ethanol, there was no purple. That wasn't an option. There were only 3 colors in this blend. Blue seemed to also travel with ethanol at the highest rate. Why? Okay, ethanol has an OH group and a hydroxyl group, so it has the ability to hydrogen bond. And so I think on blue, I can't remember where that was in the sheet. Was blue the one with the OH groups on it too? Yes or no? You have the structures in front of you. It's not like a guess and check kind of thing. The sulfite-like things. Okay, so it had a bunch of abilities for dipole attractions. Ethanol, though yes, we call it as hydrogen bonding. Anything that's polar can do hydrogen bonding. Anything that's can do hydrogen bonding, it can do also everything else. It can do a dipole because it's just a polar interaction, and also this one specifically has a pretty chunky chain of carbons, so it can also do some London dispersion with the rest of the blue. And of course, you guys are comparing it to just the blue, but in your analysis of this, you'll need to look and see why did yellow and why did red not travel as far, and you would need to discuss that regarding IMFs on each of those. And then water, blue again. Can you imagine why? Water can do double dose of hydrogen bonding. Not really any London. So was there a significant difference between the travel rate of red and yellow on the water ones? So yeah, was it the red one really low? Red one was really low compared to, I think, ethanol ethanol and acetone. All the colors kind of traveled together. They blended some, but you'll have to discuss some of that between the differences in IMFs on these versus water versus acetone. Because you got some good interactions with LDFs on these two, but water, not really any LDFs are going to be at play. Are we okay on data? Okay. My goal is for you to finish as much of the lab as you can tonight, but I know you have FRQs to do, and so we'll figure out more lab stuff tomorrow. But I need to tell you osmotic pressure. Now, ready? Close your computer so I'm not competing. Osmotic pressure. I'm only going to do 2 examples. 2 examples. Here we go. All right, osmotic pressure, osmosis should come to mind when you hear that. What is osmosis? Transfer water from high concentration, low concentration. When shall water stop moving? When it's at equilibrium. So that means that if you have a cell, so this is a biological application. Who's ever heard of dialysis? This is what they have to use. They don't know it, but they do. Essentially, you're trying to stop the water from flowing with the application of osmotic pressure. It's the pressure required to stop osmosis. And so it's the pressure on each side of a membrane of like a cell when osmosis has stopped due to the fact that you have equal quantities or concentrations of water on either side. So we're not always looking at water though. A lot of times we're looking at solvents. We're looking at like what is in the water or what's in the solvent that's, relevant with the cell. So maybe it's sodium chloride or a protein or some nucleic acid. Like it depends on what we're dealing with within the cell. But in terms of this image, this is a YouTube, not YouTube, but literally called YouTube. If I have a concentrated solution on this side and then a non-concentrated or low diluted solution over here, which way or which direction, the left or the right has more water, has a higher concentration of water? The right. There's more water here because there's less solvent. No, actually I called this solvent. I'm going to call that solute so I can stick with the example I'm going with. Okay. So if these little particles are representing solute, you said the greater concentration of solvent would be where? On the right. So the right side has a higher concentration of water or dose of water here. So which way will osmosis occur? To the left to dilute the sample over here. So that makes sense. But when will it stop moving? When you have equal concentrations of this side and this side. And so that would be what we call the osmotic pressure. It would be the pressure we'd have to apply on this side to stop the water from flowing. But more importantly is, how do you calculate osmotic pressure? It's related to the ideal gas law. So I'm going to work down here and then come back up. But it's related to the ideal gas law because it's related to pressure, it's related to concentration, it's related to temperature. Temperature is going to definitely cause things to move faster or slower. So there's a 100% correlation here. So the ideal gas law, PV equals nRT. Essentially, this is pressure of a gas. So we're talking about like in a different scenario. This is the pressure of a solution, the solvents, the pressure it's going to take to stop osmosis from occurring. So if I replace pi, which is just the symbol for osmotic pressure, it is not 3.14. Okay, we're putting pi there because that's the symbol of osmotic pressure, not a constant. I know we have so many other things to choose, but we like K's and pi. So if I rearrange this equation, pi, which is osmotic pressure, is equal to divide by V on both sides. V cancels. What's N over V? Moles over liters, which is molarity, capital M molarity. What is the R constant here if we're going to be using our favorite version of R? 0.08, 21 atmosphere liters per mole K. That means that this osmotic pressure must be in what unit? Atmospheres, if we're using that R constant, there are like 3 other R constants regarding this. They're on your reference table. If you don't convert this to atmospheres and use the other one, I get it, it's fine. Just don't make a goof and forget that units need to cancel out, okay? M is going to be what? Moles per liter, or molarity, concentration. We know what R is, and T must be in what? Kelvin. So if I give you Celsius, how do you get to Kelvin? Plus 273. All right. The only addition I have here is that I, what's I stand for? Banton factor needs to be included, because if you add a solute that breaks in or stays as one particle, that's going to cause a different osmotic pressure than a particle like aluminum phosphate or sodium chloride or magnesium chloride. All of those are going to have a different I factor, and they have a covalent structure. So pi is equal to I mert. Pi is equal to I mert. What's pi stand for? Good. No one said 3.14. Yeah. I is called the Banton factor. It's in your notes from yesterday. It's the number of particles that things break into. Okay. Determine the molar mass. So we like to do biological examples with osmotic pressure, because that is the application of this, especially with like dialysis and looking at proteins and different compounds that are inside of cells. Because they're very, very hard to isolate, we look at different features of the cell, and we can then determine information about the protein, because once you take it out of the biological organism, it breaks down and decays. So we want to determine the molar mass, okay? So in terms of finding molar mass, what am I looking for? Say again? Grams per mole. And so this is kind of the question. Of a certain protein, you have 1.00 times 10 to the negative 3 grams, so write in your givens as we go. So you have 1.00 times 10 to the negative 3 grams. It was dissolved in enough water to make a 1 ml sample of that solution. The osmotic pressure of the solution was found to be 1.12 torr. Pi is equal to 1.12 torr at 25 degrees Celsius. So what is that? So add 273 to 98 Kelvin. Okay? Calculate the molar mass of the protein. Talk first. Look at the variables you have. Utilize your equation. I will tell you most proteins are organic. They don't break down into many pieces of I is 1. Oh, if you're looking to go from torr to atmospheres, what's the conversion? 760. 760 torr is equal to 1 atmosphere. Calculating is a molarity. Moles per liter. Once you get to molarity, think about how you can get to molar mass. Molarity is not the answer. It's not final, you're good. right, come back to me. Give me a heads up on what units. Chase, answer that. Give me a heads up on what's canceling here. Tor cancels. Okay, what else? Miss Inlow's room. Kelvin cancels. Atmospheres cancel on top and bottom, so we end up with liters per mole on the bottom, which is not a thing, right? Floppy dot copy. And two. Thank you. Go in 1 second, Margaret. Just hold on. Moles per liter is going to be how that will be designated in the end, which is molarity. Molarity is not giving us anything, right? What do we need to do to get to moles? Multiply by what? How many liters? 0.00100 liters, because it was given to us as a 1.00 milliliter sample. So we back that thing up and then keep the sig figs here. And then how many moles is this? 6.02 times. So that's 3 more decimals back. So this is a -5. We go to -8. That's moles of protein. And then how would you get to molar mass of protein? Again, take the grams and divide it by the moles we just achieved. The grams were 1 times 10 to the -3rd grams. 1 times 10 to the -3rd grams. And that's grams of protein over the 6.02 times 10 to the -8 moles of that same protein, because those are like equivalent in nature. It's just they give us in 2 different separate pieces. So what's the molar mass? 16,611.3, something like that. Yes, it's big. Proteins are humongous macromolecules, so don't be scared when you get numbers like this regarding biological molecules, because they are humongo. There's a lot of stuff. And then, so how many sig figs would this be? Is it 3 at the top, all the way through? So, something like that. Okay? All right, you do exercise 12, and, like, do it now, and you're going to put laptops up. Just, log off and do exercise 12. Yeah, absolutely. It's a little easier if you don't have a micro version. Calculate 12. We're thinking the other R value.
Okay.
The other one is the joules per mole count. Oh, I hope I didn't. That's a gram.
No, it's not about it was power.
Okay, no joules. My bad. My bad. Put your laptops up, please. One, 5, 7?
Yes. Is released, and I is the branch
You guys is off.
which basically one and one ionize, it's carbon ionized. So since in a Cl can ionize 3 ions, you can have each one. Even if there's not ECl, it's still ECl3.
Dang it.